Thank you so much for giving me the chance to speak here and for organizing this. I'm here to talk about something that's really close to my heart. It's something that I'm working on or was recently working on. It's the construction of curves of high rank. So let me just jump right in with what the main statement is that I want to discuss today, which is that if you have a genus at least eight, which is congruent to 2 mod 3, then it turns out that there exist infinitely many genus G curves over Q, which are pairwise non-isomorphic over Q bar, and which have rank at least 4G plus 15, where again G is the genus of the curve. And so, just what do these things mean? Here, K above, I mean, K was a number field, but just for some definitions, for a field K, a curve over K would be a smooth projective geometrically integral one-dimensional variety over K. And the Jacobian of such an object is an abelian variety denoted J of x over k, which is going to be of the same dimension g as the genus of the curve. And if we make this simplifying assumption that the curve has a k rational point, then this Jacobian actually represents pic naught. And what that means is for every field L which contains k, the group of L rational points of the Jacobian is exactly pic naught of the base change of x to L. And here pic naught, let me remind you, is a group of degree zero divisors modulo the principal divisors. So just some examples that we probably interact with on a daily basis is assuming, of course, that x has a rational point. A genus G, a genus zero curve with a rational point is just the projective line. And so every degree zero divisor is principal. And so the Jacobian is just spec of k, so it's a single point. If the genus is one, then it's isomorphic to its own Jacobian. This is the case of elliptic curves. And so the Mordell-Weil theorem tells us that if K is a number field, then the Jacobian is a finitely generated number group, abelian group. So there's a free part and there's a torsion part. Right? And so the rank of x over k is just this integer r. It's just the rank of the free part of the Jacobian, the rank of the free part of the k rational points of the Jacobian. So here's a natural question. If you fix a positive integer g and you allow your x over k to vary over all genus G curves over Q, so it's natural to ask, does the rank remain bounded? Or equivalently, you can ask, does this following constant R of G exist? So here R of G is defined to be the smallest integer with the property that the rank of x over q is bounded by R of G for almost all x over q of genus G. And here almost all means all but finitely many x over q. And here I should clarify, it's important to clarify that this finitely many means finitely many that are non-isomorphic over q bar. And so in particular, whenever you see henceforth the phrase R of G at least C, you should just take that as equivalent to saying that there are infinitely many genus G curves over Q, which are pairwise non-isomorphic over Q bar and have rank at least C. Cool. So what is known about R of G? The existence is currently open for all positive genera, and so the most is known from what I know. The most is known in the case of genus one, where this is pretty exciting. This is one of those situations where people have conjectured both yes and no. In other words, they've conjectured that the ranks are uniformly bounded and they're not for elliptic curves. And in particular, there's two independent sets of heuristics which suggest that it should be bounded by 21. The first one due to Watkins, who credits it due to conversations with Granville. Sorry, maybe I should have written that. And the second one due to Park, Poonen, Voigt, and Wood, which is just, I believe, around a year ago. And for the genus at least two, there's no folklore conjectures or heuristics that I'm aware of. And if anyone knows something, if anyone knows of any such things, and please let me know after the talk. And so what we can do is provide lower bounds. I mean, what has been done, I mean, is we can provide lower bounds. For the genus one case, for elliptic curves, the current record is at least 19 due to Elkeys. For genus two case, it's at least 32. And here I've written it as 28 plus 4 because you get this bound by applying a method of Coulles to a high rank elliptic curve, which is the current record for the rank of an elliptic curve over Q. This is due to Elkies, and so I've written Kulesh plus Elkies. And so for genus 3, again, it's at least 26 due to Kulesh. Now, for genus at least 4, the current record is due to Shioda, who gets the bound 4G plus 7. So henceforth, what you'll be saying is always this R of G written in terms of the genus itself, because that's what we're interested in measuring. And so today I want to present on how it's possible uh, to actually improve this last record in the following bounds. So for genus equal to 5, we can improve this to 30, which is 4 times 5 plus 10. For genus at least 4, which is congruent to 1 mod 3, we can improve this 7 over here to an 8. And for genus at least 8, which is congruent to 2 mod 3, we can improve this 7 to a 15. Cool. So let me just quickly outline how this is like the game we're going to play. It's we basically take specializations, and how it works is you construct a non-isotrivial genus G curve of high rank over some rational function field. And here this is supposed to be a bold font T. I'm sorry if it's not very clear. This bold font T refers to this tuple of indeterminates T1 through Tn. And so we construct such a genus G curve having many QT points. And here we're going to be basing today's work on construction due to Mestre. And then we show that somehow we take differences of these points and look at those divisor classes, and we show that these generate a subgroup of large rank of the Jacobian over QT. And so this is the picture that we get more or less. We start with this curve over, this should be spec of QT, and then we can extend this out to a family of curves all over some open subset of the affine line, of n-dimensional affine space. And then when we take a fiber over a Q-rational point, such a thing will be referred to as a specialization of X today. And in concrete terms, if this curve is given by some equations with polynomial coefficients, they're polynomials in these indeterminates, and you just plug in rational values for those indeterminates. And so if we've got this whole setup and we've got this curve over this function field of rank at least C, then it turns out that we're already done by the theorem of Néron, Néron's specialization theorem, which just allows us to conclude that infinitely many of these specializations will be both pairwise non-isomorphic over Q bar and have rank at least as high as the rank of this generic fiber. And so we get the statement R of G at least C. So that's the plan of action generally. And so let me just remark that there are also constructions of a very different flavor. So Hammond, Skim, Logsdon, Lozano-Robledo, and Miller very recently proved R of G at least 4G plus 2, conditional on a conjecture of Nagao. And what's interesting about their method and what makes it so different from today's talk is that they don't actually produce explicit points on these curves, which is fascinating, I think. And so now I want to lead into Mestre's construction, and which is going to rely on this following key lemma. And what this lemma says is that if you're over a field of characteristic different from 2, and you start with a monic degree 2k polynomial, and your k is just some positive integer, then you can uniquely express this as the square of a monic degree k minus some polynomial that's degree at most k minus 1. And by uniquely express it, I mean that this h of k and L of, this h of x and L of x are uniquely determined by this initial polynomial that you started off with. And it's also true that generically, this remainder, I should mention, this is going to be referred to as the square root approximation of m, and this L will be the square root remainder of m. And so it turns out that generically, this thing will actually not only be degree at most k minus 1, it'll be degree exactly k minus 1. And so what that means is that for it to be degree exactly k minus 1 is some kind of open condition on the coefficients of this initial polynomial m of x. And so just an example for the degree 2 case, you start off with the monic quadratic. That's the square of a linear minus a constant. And you see that the coefficients of these polynomials are themselves polynomials in the coefficients of the original quadratic polynomial. And so for this, I mean, you can imagine that in larger degrees, for this first coefficient to not vanish is the non-vanishing of some polynomial in these coefficients of the initial m of x. And so let's just jump right into Maester's construction and see how it uses this lemma. So Maester's construction starts with a bunch of indeterminates t1 through t of 2k. Right? From that, you form this monic polynomial of degree 2k, which has as roots exactly the ti's. So that's going to be our m of x, and we write that as an h of x squared minus l of x. And again, the coefficients of each of these is a polynomial in the coefficients of this, but each coefficient of this is a polynomial in this. So basically, these are things, they're polynomials over this function field of q adjoin all these indeterminates. Right, and so what we get is a curve y squared equals L of x. That's this curve over this function field. We get this sort of interpolating function, which is y equals h of x. And it turns out that, and you can check this by substituting ti, x equals ti into this, and this right-hand side will vanish, and you'll get equality. That we started off with these x coordinates ti, and this is a projective line over this function field. And then, so Maester's construction sort of lifts these x coordinates to these rational points on this curve y squared equals L of x. Yeah. And so what have we got? We've got 2k rational points on this curve, and using those, we cook up these degree zero divisors, which is we just take twice the rational point and subtract the divisor at infinity. And what is that? That's just the pre-image of this point at infinity, which is going to be the sum of two distinct points or twice a single ramified point, depending on the degree of your curve. So we've got these degree zero divisor classes, and so they correspond to Qt rational points of the Jacobian. And so we can ask what is the rank of the subgroup that they generate. And so we notice right away that if you just examine the divisors and poles, the divisor of zeros and poles of this function y minus h of x, where I'm regarding it now as a rational function on this curve, then you see that, I mean, you get exactly this. And in terms of points on this Jacobian, that just gives this one single relation between these points, between these rational points on this abelian group, right? And so Shioda proved that in fact there's no other relations, and so we have 2k many points satisfying a single relation, and so they generate a subgroup of rank they generate a subgroup of rank 2k minus 1, which means that the rank of the entire Jacobian, and in other words, the rank of x over qt is at least 2k minus 1.
If I great. We have one question asking, saying that your method produces cursed curves for the Chaboty method. And so are there any known examples of curves having this lower bound for the rank? Is that possible? This might contradict.
So honestly, I'm not. To be honest, I have no idea which curves, if any, arise as modular curves in this method. That's not something I've thought about. But great question.
Good point.
But,
yeah. Thank you.
Yeah. Sorry. Yeah. Thank you for the question, though. Please keep coming. Great. So what have we got? We've got this curve, and we've got a seemingly high rank subgroup of the Jacobian. And so we want to evaluate what this is in terms of the genus G of the curve. And it turns out you can actually compute this genus directly from the degree of this polynomial L of x, which is, let me remind you, k minus 1. And so if you compute this genus, it works out to be either k minus 2 over 2 or k minus 3 over 2. And so this second case yields this lower bound, where again, when we apply Néron's theorem to take those specializations, we get this lower bound on R of G. It's at least 4G plus 5, which is great. And so how can we improve on this? The idea is to find a rational Q variety S inside this affine 2K dimensional affine space, such that the specializations degenerate to lower genus curves. And so the picture is something like this. This is this affine space, and this is like an open subset. If you pick a random point, you expect that the specialization will be degree k minus 1. But on this closed subset, it degenerates to something that's maybe degree k minus 2 or less. And in order to be able to apply Néron's theorem and actually get infinitely many specializations this way, we want actually to find a rational variety living inside this closed subset on which these curves degenerate. And also, I noticed that there was a challenge problem in the summer school for constructing elliptic curves of high rank, and I do believe that you can use this to construct elliptic curves of rank at least 11, and various authors, starting with Mestre, constructed curves of rank at least 12, 13, and 14, the genus 1 case. Fun fact. And right, so what do we hope? We hope that the rank doesn't drop. In other words, we still get a subgroup of rank 2k minus 1 on the Jacobian. But well, if the degree drops enough, we can hope that the genus is dropped, and in which case the rank in terms of the genus has become better. So we've produced an improvement. But of course, the difficulty is how do you find such a rational variety? If you look at the equations for this closed subset, it's quite confusing. It's not at least to me, it's not clear how one might go about finding a rational point on that thing. And so really the fundamental observation on which this entire talk hinges is this following observation, which is suppose we can decompose our k as d times e, where I mean the really non-trivial case is when e is at least 2. And suppose when we take some specialization of those indeterminates, we get something that's e comma 2d composite. And what do I mean by that? I mean that when you form this polynomial, you can decompose it as m of g of x, where the outer is degree 2d and the inner is degree e. Right? So that's what it means to be E2D composite. In other words, it decomposes as a degree 2D composed with a degree E. And so where am I going with this? It turns out that if you apply the lemma, then the square root approximation of this will look like this. Whoops, there's supposed to be a square there. My bad. It'll decompose as an h of g of x squared minus an L of g of x. And what's awesome is you can see that the degree of this is the degree of g, which is e, times the degree of L, which is d minus 1. And this is ed minus 1 minus e minus 1. But notice that if k is de, we generically expected a remainder of degree k minus 1, or in other words, a curve of degree k minus 1. In other words, ed minus 1, but we're actually getting a drop in the degree e minus 1. So we win. And this is a smiley to indicate my feelings when I notice this. And I say I notice this. I mean, but implicitly, so explicitly, I haven't seen it written down or published anymore. But I mean, we'll see implicitly that others have certainly used this exact idea. So just to do some accounting, so this is the curve we have. I'm going to denote it as x tilde. And I'm going to denote its genus by g tilde. And what we expect is if the rank hasn't dropped, it turns out that what we can expect is this lower bound on rank, which is 4g tilde plus 2e plus 3. So for instance, if you take e equals 1, we get 4g tilde plus 5, which is like the baseline lower bound on rank. And so let's see what happens when we take e equals 2. I mean, first, we need to see that we can actually find such a rational variety. And so we have here what actually turns out to be Shioda's construction. We can just take a bunch of indeterminates and we take also their negatives, right? And clearly this is going to be a polynomial m composed with x squared. And then when you go through the whole thing, I don't want to bog you down with the details, but just looking at it, you can see that when we intersected with that interpolating thing, we get a bunch of points, and in this case, you get 4g tilde plus 8 points. And Shioda proved that actually, again, they only satisfy that one single relation. And so you get a lower bound of 4g tilde plus 7. And again, by Néron's theorem, you get this lower bound. And so how do we improve this bound? It really relies on finding that rational variety which parameterizes E2D composite tuples. And so today we win by finding such a variety that parameterizes 6 2D composite tuples. And so just very quickly, what is this variety? It's basically you take this third cyclotomic field and you take a bunch of variables and you cut out by these norm polynomials. And basically you want a bunch of elements having the same norm. And why is this rational? Because it contains an open subset that's isomorphic to a two-dimensional torus plus a bunch of one-dimensional tori. And these such things are known to be rational over Q, the two-dimensional case being due to Voskresensky. And so actually this gadget is rational over Q. And so it just turns out that if we form this polynomial where coordinates plus minus si plus minus ti, roots plus minus si plus minus ti and plus minus of si plus ti, um, we get something that's 6 to decomposite, which fantastic. And we went. And so what happens? This is a degree 6 times d minus 1 polynomial. And if we denote its genus by g tilde, it's genus 3d minus 4, which is 2 mod 3. And so this is actually what we get. These are just the rank bounds, and I'm almost out of time, so I'll just leave you out to look at that. I'll just say that in the lowest degree cases, what happens is we don't quite get 4g tilde plus 15, which is unfortunate. And why is that? Because this curve y squared equals L of g of x. It has a natural map to y squared equals L of x, where L is of degree d minus 1. And so basically, if d is 2 or 3, then that's a genus 0 curve. And somehow that introduces new relations in the Jacobian and causes the rank to drop. And so this is basically how we get rank at least for g plus 15. And I believe I'm out of time, so I'll just leave this slide open, which is, if you find a positive answer to this open question, then you have a very good chance of improving these bounds. And if you actually find a rational varieties worth of positive answers to this question, then you would stand to improve that R of G bound even further. And yeah, and this is related to a classical problem of Diophantine geometry, which is super interesting and natural. I strongly urge you to go check it out. And I think that's it. So,
thank you.